All right, what we're going to look at today is a comparison of non-Euclidean and Euclidean geometry. So it's really important that you read the chapter for this material because there's a lot of information that I can't even begin to touch on the history of everything. So it's very important that you read it over. But we're going to talk about something called Euclid's postulates and axioms, and we're going to be talking about the parallel postulate, which was the big postulate that differentiated between Euclidean and non-Euclidean geometry. We're going to be talking about the origins of non-Euclidean geometry, something called topology and networks. So when we're talking about geometry, we talk about postulates and axioms, and these are basically pieces of information that we accept as being true, that we don't really feel like we need to prove as being true. Excuse me. With Euclid, he was the big creator of geometry, and that's why we call it Euclidean geometry versus non-Euclidean. So basically, Euclid had 10 postulates, excuse me, that he built all of geometry on. And one of the postulates was 2 points determine one and only one straight line. So given any 2 points, there is a line through those 2 points. And it was just something that everybody accepted, that they really didn't feel like they could prove or they needed to prove that it was a true statement. The second one is a straight line extends infinitely far in either direction, which again was just accepted if you have a line that it extends in either direction. The third one, a circle may be drawn from any given center and any given radius. So that made sense again. I could give you any point and tell you to draw a radius, a circle with that radius, and you could draw a circle with that radius. All right angles are equal. So the definition of right angles is they equal 90 degrees. So if they all equal 90 degrees, they all have to be equaled. And those four, there really was no debate on. Everybody felt comfortable with that. The fifth one, given a line K and a point P that's not on the line, there exists only one and only one line through that point that is parallel to K. So basically, again, here we're saying given a point, a line K, so here's our line K, and a point P that's not on the line, here's our point P, and I could put my point anywhere, there exists only one line, M, through P that is parallel to K. So I can only draw one line that goes through P that is parallel to K, and we'll call that M. And that's called the Playfair's axiom. And that was the one point that tended to challenge people. Things equal to the same thing are equal to each other. So if A is equal to B, then B has to equal A. So basically, they're equal to each other. Or A is equal to B, B is equal to C, then A is equal to C. Number 7, if equal things are added, then their sums are equal. Okay? If equals are subtracted, then the remainders are equal. Figures that can be made to coincide are equal. In other words, if I can lay one shape on top of another shape, then and they are identical in size, then they are equal to each other. The whole is greater than any two of its parts. So if I take any item, here's my segment, and I divide this segment into 2 parts, okay, the whole piece is greater than the 2 small parts, either one of the 2 small parts. And everybody was fine with those 10 axioms, but the 5th one, the parallel postulate, everybody tended to argue with. And one of the reasons they argued so much is you'll notice that all of the other 9 are very short and simple and to the point. 2 points, you've got a line. A line goes in any direction infinitely. Given a point and a radius, you got a circle. But what you see here is actually Euclid's entire 5th postulate. And it says, and I'll read it, you can read it yourself. In its original form, it states that if 2 lines, K and M, below, are such that a third line, N, intersects them, so that the sum of the 2 interior angles, A and B, on one side of the line is less than the sum of two right angles, then the two lines, if extended far enough, will meet on the same side of n that has the sum of the interior angles less than the sum of the two right angles. So you can see very simply that this is very wordy, very long, and very complicated. And so the more complicated you make something, the more likely it is that somebody's going to want to come in and try and prove that it's wrong. And that's exactly what happened. And hence came the development of what we refer to as non-Euclidean geometry. And so with non-Euclidean geometry, basically all of the non-Euclidean philosophies challenge that fifth postulate. They challenge the fact that there is one line parallel to any given line. And that's the whole point of non-Euclidean geometry. So one of the first challengers that actually published his work, and a lot of people challenged it, but they didn't have the nerve to publish it because they were afraid of challenging Euclid and challenging the system. But there were a few that did decide to go ahead and challenge it. And this first one, Lobachevskian Geometry, challenged it. And basically all of Euclid's theorems were based off of the idea that we have a rectangle and that these two angles are 90 degrees. So with Lobachevskian, he felt like instead of those two angles being 90 degrees, if you look at these angles here, he felt like the angles were less than 90 degrees. He felt like they were less than 90 degrees. So if you think about having a triangle, then the value, you know, we always know that the three angles of a triangle equal 180 degrees. But if these two angles are less than 90, if I add them all together, I'm going to get a value that's less than 180 degrees. So Lobachevskian believed that through any point P that's not on the line, there are two different lines that can be drawn parallel to K. So what you've got to visualize is that the challengers to Euclid's theorem did not believe that things were flat. They did not believe that the earth was flat. And in Euclid's time, they were still believing that the earth was flat. And these challengers were coming through and saying, no, we don't think the earth is flat. We think it's round. And if things are round, then there could be other lines that are parallel to that line if you think about the universe being rounded. And so that's what these challengers were doing. And he believed, Lobachevskian believed this idea of what we refer to as a pseudosphere. In other words, not a flat surface, but this idea of, you know, having a rounded area in the middle, but things tapering off the ends. He believed that the sum of any, the measures of any angles in the triangle is less than 180 degrees, whereas the Euclidean theory was that they equaled 180 degrees. So these are just some of the challengers. These challengers actually came up with proofs of these things, but their proofs were challenged by the Euclidean theories, and it was really hard to prove to people that their theories were right unless people were willing to take an open mind, think outside the box, and not think of the world as being that flat Euclidean surface. Riemann geometry came through with even some more ideas, and he even used the sphere idea more, where he thought of all the lines, what we think of as lines in geometry, are really just circles, and they're circles that go through the center of the sphere. Basically, if you want to think of the equator as a great circle, he was imagining that there are an infinite number of great circles on the earth, and so his idea was that you don't really have lines, you have parts of these great circles. And if you think about the real world, it sort of makes sense. You know, in our little space in this world, it might make sense that from point A to point B is a straight line. But if I'm on one side of the world and you're on the other side of the world and you think of drawing that line from A to B, is it really a straight line or is it an arc? And so that's what Riemann geometry was philosophizing, that we're talking about arcs and we're not talking about lines. So he replaced the fifth postulate with, through any point P not on line K, that no line can be drawn that is parallel to K. And he philosophized that the sum of the angles of any triangle is more than 180 degrees. So, and again, he went through and he did quite a bit of proof to try and prove his theorems, but it was very difficult to prove his theorems when people were still thinking of the Euclidean geometry that they were familiar with. So there's been a lot of talk in the news, not too recently, about Euclidean and non-Euclidean geometry, and people are still trying to prove these non-Euclidean theories. And they're still coming up with the same challenges, people challenging the idea of why are you trying to change geometry. So maybe one day we will be looking at this new kind of math, just like we looked at new math back in the 70s and 80s. So another area of geometry is what we call topologies. And topology is studying like how the things are distorted and bent and scattered and torn. They talk about number of holes in an object. So for an example, if we were deciding whether a donut and an unsipped coat are topologically, so are they the same equivalent? So to try and figure this out, they would look at how many holes are in the object. Well, a donut has one hole and an unsipped coat has two holes, one for each arm. So the donut cannot be twisted and stretched into the same as the coat. So they are not topologically equivalent. Sorry, I had a problem with that word a minute ago. Another idea would be something called genus. And when we're talking about genus, we're talking about how many cuts can be made, and this is an important concept, without cutting the figure into two pieces. So when we're classifying things, we classify things based on this genus. So for example, the things in the first column have a genus of 0. If you look at the box, we made a cut across the top of the box. We made one cut. We opened the box up, but we did not separate that one cut did not separate the box into different pieces, into two different pieces. On the second one, if I make one cut here, then I have cut the pencil into two different pieces, so it has a genus of 0. If I make one cut on this fork, I have cut the fork into two different pieces. It has a genus of 0. If I make one cut on the hammer, I've cut it into two different pieces, so it has a genus of 0. On the donut, if I make one cut here, I have not cut it into multiple pieces. So the pencil has a genus of 0, a genus of 0, and a genus of 0 on the hammer. But the donut, I can make a cut, and I have not cut it into two pieces, so it has a genus of 1. The bolt would be the same thing. The cup, I could cut it right there, and I haven't cut it into two pieces. I'm not sure exactly what that last shape is there. On this last one, in order to cut it into two pieces, I could make more than one cut, so it has a genus of 2. I would have to cut the middle of the pretzel. On this one, I could cut down here, and I could cut across the bottom of the cup, and I still haven't cut it into two pieces. So these are just ideas of what they mean by genus and how you can figure out the different cuts. All right, the last topic that we're going to talk about here is something called networking. And this is a very big topic in geometry, and we're talking about different paths. And a big proponent of this type of study is somebody called Euler. And what Euler did was investigated the different ways to traverse different paths. And it doesn't sound like a very important topic, but when you look at what they do with this, for example, if you're trying to figure out what is the easiest bus route that you can make so that the shortest number of overlapping roads are crossed. In other words, you don't want to keep going up and down the same streets. You want to avoid duplicating your paths. So what we're talking about is different networks. Euler, the big thing that he started was there was the Koenigsberg bridge problem, where there were bridges that connected two islands, and they were trying to figure out how many different ways could they traverse those bridges to get from one side to the other. And this was actually a big problem, and Euler became involved in that, and that's where this networking idea started. So there are different paths that you can take, and those are usually arcs. And there are different points where these arcs come together and meet, like intersections and roads. And they're called vertices or nodes. So a network is just a set of arcs and these vertices or nodes. When we're looking at the vertices, we want to look to see whether there's an odd number of intersections or lines coming into the road, or whether there's an even number of intersections. In other words, if you've got a typical intersection at the corner, it's considered to be three, and it's considered to be a 3 number vertice, because there are 3 different points coming in together, 3 different arcs coming in together. So when we're looking at whether or not we can traverse that path, again, we don't want to overlap roads, so we want to cross each path only one time. And when we're looking at the traversability, we're looking at the different vertices to see whether they're odd or even. So there are 3 rules here. The number of odd vertices of any network is even. In other words, we're going to count each vertex and we're going to see, is it odd or is it even? And if the number of odd vertices or nodes is even, in other words, if there's 2 of them, or there's 4 of them, or there's 6 of them, then we consider that to be a good situation. A network with no odd vertices can be traversed. Okay, so if there are no odd vertices, then it can definitely be traversed. And a network that has 2 odd vertices, or more than 2, more than 2 odd vertices definitely cannot be traversed. So let's look at an example. So we want to look at whether this network can be traversed. So if we look at E, its value is 2 because there are 2 roads coming out of E. A has a value of 3. 1, 2, 3. C has a value of 3. B has a value of 3. And D has a value of 3. So there are 4 odd vertices and 1 even vertice. So if we look at the third rule says a network with more than 2 odd vertices cannot be traversed. So now going back to this, I have 4 odd vertices, so I know that this network cannot be traversed. Okay, so this next screen is blank because I'm going to draw the picture for you. So let's say my network looks like this. Okay, there's my network. And I want to know if I can cross every single one of these points and never overlap a line. Well, this vertice has a value of 2 because there's 2 roads coming out of it. This one has a 2. This one's 3 because remember we count the in, the up, and the out. This one is also 3. This one is 2, and this one is 2. So if we look at the third rule, there are not more than 2 odd vertices. We have 2 odd ones, and we have 4 even ones. So since there are only 2 odd vertices, and the number of odd vertices is even, 2 is divisible by 2, then this can be traversed. Okay, so how can it be traversed? If I start at this point right here, and I travel up, and then I travel left, and then I travel down, and then I travel across the bottom, and up this side, and over here, I have covered every single face of this shape, and I have not overlapped any of the sides. So that's considered to be traversable. Sorry. Oops. Let me fix this real quick. Okay, so let me go back and write that down. So this is considered to be traversable. All right, so here's another question. I want to know, is it possible to travel through this house going through each door only once? Right, so that means I could start here and come up through here, and I've gone through each of those doors once. I can go through here, I can go up through here, and I can go through here. So I started in room E, then I went to room A, then I went to room B, then I went to room D, and then I went to room C, and I went back to room B. So I touched every single room one time, and I did not go through any of the doors more than once. So let's look at this. So that's exactly what we're going to do. We're going to start, we're going to look at the number of rooms here. Room A has 2 doors, so it's an even. Room B has 3 doors. Room C has 2 doors. Room E has 1 door. And room D has 2 doors. So I have 2 rooms with odd numbers. So I have only 2 odd vertices. And I have an even number of odd vertices, so I am able to traverse this path and get from one place to the other. And I had already shown you what that path was. So I started at E, I went up through B, down here, back up to C, and I ended up back in B. So I touched each door only one time, and I did not overlap any of the doors. I hope this helps. Make sure you read this section because there's a lot of information that talks about the history of the Euclidean and the non-Euclidean geometry. Keep in touch with me and let me know if you're having any problems. And I hope you have a great week. Talk to you later.